Okay, thank you very much for joining us today. My name is Vincent Britz, or Vince for short. I work at Flownex International in a development role and then also in a high-level technical support role. What I'd like to talk about today is some work that I was involved in developing, is in adding some new functionality to Flownex with the aim of modeling gas turbine lubrication systems. So I'd just like to talk you through the methodology of like what we've added, and then also show you a simple demonstration as to how we can go about building these models. Just before we talk about the technical details, these are just a couple of applications or uses that I see for this type of model. The first of which being the sizing of oil scavenge lines. So not only just deciding on the diameter in this case shouldn't be too small because the required oil flow rate will correspond to a particular cooling load. And then along with that, if the pipe is too small, you would not be able to achieve that cooling flow rate. And if the pipe is too large, you could be wasting precious space in your gas turbine engine. So sizing that line is important, but then also above and beyond that, determining whether or not it's sufficient to have that line configured as a gravity-fed line, or whether or not you should be installing a scavenge pump, some kind of positive displacement pump like a gear pump, in that line to just create that additional flow inside of that particular line if space is such an issue that the pipe diameter can't be large enough for a gravity-fed flow. Another application would be in analyzing the air side. So these bearing chambers are sealed by air around the shaft itself. In that case, it's important to know the secondary air consumption for the purpose of designing secondary air systems. So working out what that secondary air flow rate will be would be a good application. And then also looking at sizing the vent lines. In the case that you have a bearing chamber that has an air vent, sizing that vent line is important to ensure that the level inside of that particular chamber is at the value that you would like. And then the last thing is looking at some startup scenarios. So as with all of our models in Flownex, we have the ability to run steady state as well as transient simulations. So we could look at varying the air supply pressure during the startup of the gas turbine and understanding what effect that has on the oil cooling or the cooling oil flow rates, and seeing how the entire system behaves with these varying conditions. Okay, so just to talk briefly about what the latest Flownex release this year included. So there are a few other things outside of this, but these are the two main sections that are related to this webinar. The first of which is a new fluid type. It's a liquid gas fluid type. It basically allows us to mix a incompressible liquid with a compressible gas fluid, and we just specify them as a standard liquid fluid and as a standard gas fluid. There's no need for any complex fluid properties. In the past, we've tried to model similar applications where we have a two-phase fluid mixed with a gas. We've had this model, we call it the two-phase incondensable model. We've had this in Flownex for a while now, and we use it for humid air applications. We looked at using it for this particular application, but specifying oil as a two-phase fluid required very detailed two-phase fluid properties for the oil, which really isn't practical. So this fluid was created to basically fulfill that need, and allows us to mix just a standard liquid with a constant density, for example, or a density that varies with temperature, and then simple specifications for viscosity, conductivity, density, and specific heat. And with that information, your mixture can become fully defined. To go and actually assist in predicting these pressure drops as accurately as possible, we also added a new two-phase pressure drop correlation to our pipe components. We added the Beggs and Brill correlation. This correlation allows us to account for the pressure drop using a non-homogeneous momentum model. I'll talk a bit more about that later. and is widely used in the oil and gas industry for predicting the pressure drop in pipes with two-phase flow. And then secondly, we also added another correlation to our bend components. This is the CRISM model, and is also used for predicting two-phase pressure drops in bends. Just a little bit of information on this Beggs and Brill correlation. This is fully documented in the new Flownex release. So if you do have a copy of the software, you can check it out in the Flownex theory manual. Alternatively, if you'd like to know more information, please let me know and I will send that that entire section onto you, where you can read through all of the details as to how this pressure drop is calculated. In short, basically what this correlation does is it first classifies the fluid into a particular flow regime. The Beggs and Brill correlation has 4 different regimes, namely distributed, segregated, intermittent, and transition flow. The regime is determined by looking at the combination of the fluid number and the input liquid content or liquid holdup. This liquid holdup is basically the volume fraction of liquid. Once this flow regime has been determined, we're then able to calculate the liquid holdup of the fluid, or the actual liquid holdup. That input liquid content is considered the homogeneous liquid holdup. So that assumes both velocities are the same. The correlation then corrects this liquid holdup, creating what is called the actual liquid holdup. And this is calculated taking into account the inclination of the pipeline as well. This particular model then also allows us to have separate gas and liquid velocities and provides more accurate pressure drops when you don't have almost equal fractions of liquid and gas. So when you have a pipeline with very little liquid and a lot of gas, or vice versa, you can have the 2 phases at very different velocities. So this model then is more accurate in those particular regimes. Okay, Flownex itself has many components dedicated to modeling secondary flows. These will be rotating channels, rotating nozzles, cavities where we have 2 rotating surfaces, or cavities where one surface is stationary and the other is rotating. We have components for rotating annular gaps, etc. And all of these components can be used to model the secondary flow paths in these gas turbine engines. And the same secondary air that's used here is then used to seal the bearing chambers in our oil lubrication systems. So we can use the flow interface components. You'll see them under the nodes and boundaries section. They're called flow interface primary and flow interface secondary. What that allows us to do is to connect these 2 networks of different fluid types and just exchange information for pressure, temperature, and mass flow. So it basically ensures mass and energy balance across that boundary, and then allows us to connect these 2 systems with different fluid types. So you can connect your secondary air system directly to your lubrication system instead of having to transfer boundary conditions between departments. You could basically set up a secondary air simulation, set up a lubrication simulation, and then connect them with these interface nodes to have Flownex deal with the data transfer between the 2 automatically. I'll show you this in detail in a second, but this is basically all we need to do to specify our oil mixture. We select the fluid we'd like to use as the gas phase and the fluid we'd like to use as the liquid phase, and then Flownex calculates all of the mixture properties under the surface. So we've put a lot of work into things like the mixture densities, mixture viscosities, how each of the components with their typical theory should then use these fluid properties. And yeah, basically the detailed work regarding this fluid model is all done in the background. From the user point of view, you would create your mixed fluid, and then some components will have additional inputs. I mentioned the pipe component has a new pressure drop correlation. So there will be a drop-down list that will allow you to choose the old correlation, the Lockhart-Martinelli correlation, or to use this new Beggs and Brill correlation. So some components will have new inputs, but most of the time when you're using the new fluid, you won't even see any difference in your component inputs. It's just the underlying fluid theory that's being applied differently. Okay, so let's move across to Flownex and I'll show you what we've got. What we have over here is a simple oil sump. We have a shaft in the middle with 2 lab seals on the left and 2 lab seals on the right. This inner casing represents the oil sump itself, or the actual bearing housing. And then around that is the casing, which allows us to have our secondary air injected for the purpose of calculating our, basically have our secondary air injected for the purpose of sealing our bearing housing. If we look at the internals here, we have our oil entering from the top. In this case, it's 2 streams just above each of the bearings. We model the inlet nozzles just with restrictors. We have our air vent on the left over here, also being modeled with a restrictor. At the bottom, we have our scavenge line. This here is our pipe component, and this pipe component has this new Beggs and Brill correlation selected. And then just some lab seals to model, as I say, the labyrinth seals at the inlets to the bearing housing, and then also the casing that allows us to pressurize this cavity with secondary air. I've used typical values for temperatures and pressures. These are not very accurate values, but they're in the right area. So in imperial units, this is around 600 Fahrenheit and around 21 psi, 22 psi. And the flow that we're seeing over here in terms of air is about 331 kilograms per hour. So in pounds per second, that's 0.2, or pounds per minute is 12 pounds per minute there. On the oil side, we have oil added about 1.5 kilograms per second, or about 3 pounds per second, and then added at a temperature of around 140 degrees Fahrenheit, or 60 degrees Celsius. Okay, so when it comes to actually modeling the interface where we have our oil and air, what I like to do for this particular arrangement is to use the container interface components. Here we're modeling the air in the top container and the oil in the bottom container. The reason I like to do it like this is firstly because the top container will then have a separate temperature to the bottom container, which means that our air phase will not share the same temperature with our oil phase, so we will be able to still have a difference in temperature, which is important for calculating the correct pressure drop of the outlet here. If we were to use, say, a 2-phase tank instead, then the air and oil phases would become the same temperature, and our air leaving would be significantly cooler. It would be as if that air had mixed homogeneously with the oil and then left at the same temperature as the oil. So this way we can maintain our air temperature. Also on the container interface component, we see a force imbalance result. So what we've gone and done here is varied the pressures inside of these components until we have a 0 force imbalance. That basically means that the pressure in the air and the pressure in the oil is the same. When it comes to building this model, first up would be in deciding on an oil flow rate. That is simply just by specifying a mass source at the inlet. We then specify our outlet conditions for our oil. Here it's just the pipe, a restrictor, and some pressure at the outlet of this pipeline. This later on will be connected down to a scavenge line and ultimately a scavenge pump, but I'll get to that in a few minutes. Once we have this all set up, we can look at what our oil phase pressure is. So in this case, we see 117 kilopascals. That is around 17 psi. What we then want to do is go ahead and connect that, or rather have the air phase pressure now made equal to the oil pressure, which would then result in a steady solution. If this wasn't the case, if for example the oil phase had a higher pressure than the air phase, we would see the level in the tank increase until the oil flow or until the oil pressure had decreased to match the air pressure. Okay, if we carry on, the ways that we can actually achieve this force balance or pressure balance is to ensure that the oil flow out is such that the oil, either the oil pressure matches the air pressure, or what I think is a better solution is to change the air side to ensure that the air phase is at the same pressure as the oil phase. So to do that, we could either change the clearances on our labyrinth seals at the inlet. Making those clearances bigger or smaller will change the pressure inside of the cavity. Or what I think is a better option is to change the size of the hole at the air vent. By changing that size, we can also change the pressure inside of this cavity. So for example, if we had a hole of say 15 millimeters, that's, if I put that into inches, is roughly 0.6 inches. That will result in a force imbalance between the air phase and oil phase. Here we see the oil pressure at 117 kilopascals and the air phase at 114 kilopascals. So in this case, our air phase is a lower pressure and we see a positive force imbalance. To overcome this, we could either increase the clearance on our labyrinth seals to have less of a pressure drop from our secondary air into our bearing housing or bearing chamber, or alternatively, we could increase the pressure drop at the outlet, basically make this hole smaller. So I think this is an easier way to achieve the same result. And in terms of design, it should be easier to achieve a smaller hole here rather than changing the clearances on lab seals. So here, if we go ahead and change the size from say 15 to 11 millimeters, we can see our force imbalance is almost zero. If you want to get it all the way to zero, you can go ahead and use the designer inside of Flownex. Here we would take the force imbalance result on the container interface component, just drag this into the equality constraints, set the target value as zero, and then drag in the size, the diameter of this outlet or this air vent outlet, and have Flownex change that size automatically until we see a zero force imbalance. So here I'm just running the designer, and after a few iterations, we can see Flownex gets to a diameter where the force imbalance is 0 newtons. So this would be one way in which we could go about sizing the air system after determining what our desired, or after implementing our desired oil flow rates and then sizing our air system to match that. In this particular example over here, what I've gone and done is implemented a small amount of carryover air into our oil stream. So like I mentioned earlier, oil is in this bottom container and air is in the top container. I haven't connected the restrictor at the outlet directly to the bottom container. Instead, I've used these flow resistance components. They are just, in this case, just connection components. They pose no real pressure drop. They have a very high admittance, so a very low resistance. You can see the pressure drop here is in the order of 1 times 10 to the minus 6 or 1 times 10 to the minus 9 kilopascals. So very insignificant in the whole system. And you can't see it too clearly, but if I highlight it, you can see that there's a data transfer link between these two components. What I've done is connected this flow resistance component from the outlet tank to the restrictor. So this flow will be calculated through the momentum conservation, whereas the flow on this component I have fixed using the fixed mass flow option. By doing this, I'm able to then use a data transfer link and specify a particular multiplier or a fraction to multiply our mass flow in this oil line by and apply that mass flow in our air. In simple terms, what that does is it takes the oil flow rate, whatever the momentum equation works out the oil flow rate to be, and then multiplies it by a percentage. In this case, I've chosen 0.1%, and applies that amount of air into our oil stream. So in this case, it's representing 0.1% of the mass of oil being air in this case. So we'll see our mass fractions at the outlet, or sorry, not 0.1, 0.3%. So here we see 99.7% oil at our outlet and 3% air at the outlet. This basically gives us a way of manually adding a small amount of carryover air into our system. It's not the perfect solution. We're still working on developing additional theory to help predict this carryover air a bit more accurately. But for now, this is a way of at least accounting for this carryover air in a relatively easy to use fashion. until we can have more detailed theory applied in these components. Okay, if we look at the pipe components, I mentioned we have this new Beggs and Brill correlation. With that, we can see additional results. So we'll see the flow regime that's predicted. If you remember from earlier, there was that flow map determined between the Froude number and no-slip liquid holdup. Using those two values, we determine the flow regime. In this case, it's intermittent flow. And then from there, we can also determine values like the gas velocity, the liquid velocity, the void fraction, basically the volume fraction of gas, the liquid holdup, which is the volume fraction of liquid, the liquid density, the gas density, etc. So we have this non-homogeneous momentum model inside of the pipe. So we're accounting for separate velocities in our two phases. Okay, so if we then move on and go and put this into a large system, what I have over here is a simple demo for a typical gas turbine lubrication system. We have two bearing sumps. I've just chosen two to keep the model simple as possible. We have a oil filter. We then have the oil flowing through a heat exchanger where the oil is cooled by air. We then have another heat exchanger where the oil is cooled by fuel. Basically, heat is transferred from the oil into the fuel to warm the fuel and cool the air. That oil then flows up through piping, through some last chance strainers, and then into the bearing sumps. The first bearing sump over here is pretty much identical to what we had before, where we have an air vent and a scavenge line, and then the bearing sump on the right-hand side has a scavenge line but no air vent. So here we have both oil and air being carried down the pipeline. These two scavenge lines then flow towards a series of scavenge pumps. So here I've modeled them using the positive displacement pump component. These here just take standard positive displacement pump charts, so volume flow versus speed, and then each of these lines is at a different pressure rise or different pressure differential over our component. If we then look what happens from here, this oil then flows from the scavenge pumps into the main oil reservoir at the top here. This oil reservoir is also connected to this other oil sump or small oil reservoir where the air is returning from that vent line. If we zoom out a little bit, we can see the air from this first bearing cavity. The air can flow up through this vent line and then through a strainer into another small storage tank, and then from there the air can pass into this main reservoir, just flowing through a check valve first so that there's no return flow in this direction. We have a small vent to atmosphere modeled over here as well, just with a restrictor and a pressure boundary condition. And then this tank here represents our oil reservoir, which is then connected through some more piping into our main oil pump. This here provides the pressure rise needed for overcoming all of the resistances in our oil system, which is primarily our oil filter, the heat exchangers, and the inlet nozzles for injection into our bearing chambers. So if we follow the flow from here, it goes through the oil filter. We have a pressure relief system is modeled as well. This basically just ensures that we don't have any overpressure in our system. The fluid then flows through the piping, through the air heat exchanger to cool the oil, through the fuel heat exchanger to warm the fuel and cool the oil even further, and then straight back up through our last chance strainers and into our bearing sumps. Here I've used the same approach as before, using the container interface to model the air and oil phases separately, and then using a data transfer link and a fixed mass flow to account for some carryover air into our oil stream and our scavenge line. On the right-hand side, I've just used a two-phase tank. Here we have our oil and air mixing. This two-phase tank basically will do a mass balance between the air and oil phases and ultimately determine what the homogeneous level inside of that tank will be. So here we see the homogeneous void fraction being 95.7% air, which corresponds to about 4.3% liquid inside of this tank. Different values or different combinations of air and oil will result in different homogeneous levels inside of this tank. This then flows through the series of pipes. All the way along, we apply elevations to the nodes to correctly account for the elevation pressure drops. The Beggs and Brill correlation, as I mentioned earlier, accounts for inclination differences in the pipeline and is one of the only correlations that is suited for all inclinations. You will find some two-phase correlations that are ideal for horizontal flow, other ones that are ideal for vertical flow. The Beggs and Brill correlation is suited for all inclinations, so it makes it an ideal correlation for this particular application. So here we specify our elevations of the nodes along the way, and then specifying the lengths and diameters of all of our pipelines. For the pipe components, we've gone ahead and discretized these components. Most importantly, from a discretization point of view, we're looking not so much at the change in fluid properties in the sense of, like, say, density or perhaps viscosity, but more in the sense of the flow regime inside of the pipeline. As the flow reaches or travels down the scavenge lines, we have the air phase expanding, and as a result, our air velocity will go up and our liquid velocity will go down. Our liquid velocity will go up as well. And as a result of that, we can have regime changes in the lengths of these pipe components. So for use with this Beggs and Brill component, we just recommend also incrementing your pipes inside of the scavenge lines. This is just going to help predict that regime change inside of a pipe component instead of just having one regime in one pipe transferring to another regime in another pipe. It's just more accurate to have that regime change in one of these pipe components. Okay, so then once all of this is set up, we can go ahead and solve our network. Let me actually talk for a second on this. On the major pressure drops, we have this oil filter over here, which I've modeled just using a general empirical relationship. You can realistically use any of the custom pressure drop components. Here I'm just using the general empirical relationship as a pressure drop coefficient. And then our heat exchangers here are modeled using the heat exchanger component in Flownex. So this is allowing us to specify the heat exchange in a very simple fashion using effectiveness. We could also specify this with, say, a UA value, but ultimately this is just a very crude way of approximating the heat transfer. If you would like some more detail, it is also possible to use the heat transfer components. So model it fundamentally using convection and conduction if you wanted to model the heat exchanger in more detail. But that would obviously require more information regarding the geometry of these particular heat exchangers. But would then give you a much better understanding as to the performance of the heat exchanger in general. Okay, so once we've gone ahead and solved this network, you can see our solving times are comparable to other Flownex networks. Here we're seeing a solving time in about 5.5 seconds. I'm using a standard desktop computer here. It's just a laptop with an i7 processor, 7th generation, so nothing fancy. We're solving this network with about 190 flow elements and about 190 flow nodes. So roughly 200 nodes and elements inside of our system. So the number of variables that we're solving for is not that many, nothing comparable to, say, 3D CFD. And as a result, we get solution times in around in a matter of seconds. So depending on the size of your network and any other fluids that you may add, for example, if you had a two-phase fluid with natural circulation, you could increase your solving times just due to the complexity of the equations that are being solved. So we're typically going to see solving times in the order of, say, 1 second to 60 seconds, just to be conservative. When it comes to transient models, we're looking at real-time or close to real-time solution speeds. Once again, depending on the complexity of your model, the physics that's at play inside of the system, and then also the time steps that you use. Okay, so just to conclude, this new Flownex release has the ability to model liquid gas mixtures. So we can connect our liquid fluid to our gas fluid with the simple specification of a liquid and a simple specification of a gas. No requirement, no need for any complex two-phase properties. And this basically allows us to build these lubrication system models, which we can then use in steady state and transient. These lubrication models can be connected to our secondary flow models, so we can actually have the actual inlet pressure for our lubrication model calculated with the secondary air system and have the mass flow rate of air consumed by the lubrication system calculated by our lubrication model and sent to our secondary air system. So both of these models can be modeled in Flownex and solved simultaneously. With this functionality, it should allow easy sizing of pipelines. This will be our scavenge lines, both from a point of view of determining the required diameter for the desired flow rate, but then also looking at the effect of gravity-fed pipelines and determining whether or not a scavenge pump will be necessary. We can then also look ahead at sizing airlines to ensure that we have pressure balance inside of our bearing cavities, and then also sizing pumps as well. In this particular example, I was using the pump components with charts, but realistically, you could just fix the mass flow in a pump component and have Flownex calculate the required pressure rise and volume flow, and then select a relevant pump that matches that performance. Yeah, so that's about it in terms of the content. If you have seen anything here that is of interest to you or something that you'd like to try out, feel free to get in touch with us. We'd be more than happy to prepare a more specific demo to your company. So if you're looking at using Flownex for your lubrication system models, we'd be happy to set up a more specific presentation talking to particular points that matter to your company or your department. And if you would be interested in trying the software, we're happy arranging a trial as well. We have resellers in North America who'd be more than happy to meet with you and chat. But then from a development point of view as well, we're also very involved with our clients in terms of adding new functionality. So if there is anything here that you've seen and you know particular correlations or particular theory that would enhance these particular models, please feel free to send us an email. The user feedback is a really strong factor in driving development here at Flownex. And ultimately, at the end of the day, these basically the input from users in industry just strengthens the usefulness of the code and ultimately benefits you and your work at the end of the day. Okay, that about brings us to the end of the webinar. Thank you for your time. As I mentioned, if you do have any questions, feel free to contact us. And then if you do happen to find yourself in Norway at the Turbo Expo next week, there is a Flownex booth there. Some of my colleagues will be across there. And if you would like some more information on this oil lubrication system, or maybe you would like to try out the software, they'll have Flownex up and running there, and you can chat to them, ask as many questions as you would like, check out some of the models, for example. So yeah, if you are there, please stop by. We'd be more than happy to meet you and to talk about some of these applications. Okay, that brings us to the end of the webinar. If you do have any questions, please type them into that questions box, and I'd be happy to answer them.